Hi everyone, welcome to the talk Privacy Preserving Netting in Local Energy Grids. This work has been authored by Marco Peise, Dongha Kim, Stefan Tai and me, Jakob Eberhardt, and we are from the Information Systems Engineering Group at TU Berlin. The goal of this talk is to provide you with an overview of our work and to make you curious to read the paper. Of course, we had to simplify now and then, and you can always go back to the paper for further details. As you can see from the title, this talk is about a blockchain application in the context of the energy domain. More generally, from a computer science perspective, though, we will show how verifiable off-chain computations in combination with commitment schemes can be used to execute computations with blockchain properties, but without giving up privacy. We will proceed in two steps. First, we motivate our use case from an economic perspective and derive a technical problem. Secondly, we develop and implement a technical solution to that problem and evaluate our solution in the context of a large German national research project. Let's jump right to the matter. We'll describe the community energy sharing use case in more detail and then derive the problem statement that we will later address technically. For a bit of context, climate change is one of the greatest challenges of the century, which is commonly agreed on by now, and increasing production of other kinds of renewable energies is crucial to address climate change. We need more solar plants, more wind energy, more water energy to address the growing need for energy globally without using fossil fuels. Small-scale production, however, is oftentimes not economically viable. And without subsidies, in many cases, plants get shut down and they cannot be operated profitably. There are, of course, existing approaches, as this has been a pressing issue for a while. And one kind of approach is peer-to-peer energy trading, which is often combined with blockchains. How it works in most proposals is that energy is traded, future energy flows are traded on an open public market. And households directly buy and sell energy on those public markets. The blockchain acts as an order book here. It matches buyers and sellers and makes sure that the buyers and sellers and other participants in the markets do not have to trust anyone but the blockchain. So that's where the blockchain comes in the first place. These approaches do have their issues whatsoever. For example, future load profiles for individual households are hard to predict. People don't really know when they're going to turn on the washing machine or watch TV, for example. So this is a bit hard for individuals to do. Furthermore, individuals have to publish very sensitive data on that marketplace for it to work. So that means other people watching the marketplace can derive individuals' plans or future behaviors in a very detailed and privacy violating way, you could say. Also, these approaches commonly take a greenfield approach. That means they don't really consider current physical hierarchical infrastructure and its limitations, or regulatory frameworks, or national idiosyncrasies that apply to these energy markets. Let's have a look at how local energy trading and the energy market from an end consumer's or household's perspective looks like today. There's an electric utility, and that company sells energy to households, and households that produce more energy than they consume, they sell to that electric utility. And the utility buys energy and sells energy, but it has a certain margin, so it sells for a higher price than the price it buys for. And it benefits from that profit, from that margin between bid and ask prices. So what if in a local energy grid, which is usually called the local distribution network, we have a community-based approach where the households can share energy they produced and don't need at that moment in time with other households. It does not necessarily have to be sold. That's a separate issue. So together the households form a community and they share energy they produce internally. This reduces the amount traded with the electric utility significantly because the electric utility will only have to provide the residual energy that cannot be generated within the local community. So what these households do together is to internalize the economic utility that was before that captured by the electric utility. So now we have a situation where a local community shares energy among themselves and they only trade residual energy with the electric utility. However, one question remains. How should energy produced in the community be distributed among the households in the community? And here is where our first contribution comes in. We propose a netting algorithm that calculates a distribution of the produced energy to consumers within that local community. The algorithm has several nice and important properties. You can see the algorithm itself on the right, but for now we'll just focus on the properties. The algorithm always ensures correctness. That means that the consumed energy equals the produced energy and it cannot appear out of thin air, for example. It also guarantees Pareto efficiency. That means nobody who participates in the community energy netting approach can ever be worse off than if they didn't. And as a last but very important property, there's fairness. And that means that the allocation of produced energy is somewhat fairly distributed to the consumers in the network. And one example of how this can be done is, for example, let's say we distribute the produced energy in proportion to the consumption of the consumers in that network. And that is one notion of fairness. We argue about that in more detail in the paper. So we have this nice netting algorithm now, but one big issue remains, and that is who calculates the netting in that community. The electric utility is usually not trusted, and neither do households trust other households. In today's system, I can be sure that everything happened correctly just by checking my local calibrated electricity meter. It serves as a trust anchor and authoritative record, and in case any dispute comes up, I can refer to that. However, the local meter reading is insufficient in our sharing case. Netting of energy in the community happens virtually and basically for accounting purposes only, and therefore it's not captured by our electricity meter. So what we need is the equivalent of a calibrated electricity meter for households in the community. So this does sound like an optimal use case for a blockchain-based solution. We have mutually distrusting parties and calculations happen on a shared data set. It will result in all participants trusting the results and an immutable audit trail to be established. So what would that system look like? We'd have a smart meter and it signs data, and then it sends that data to a household processing unit. And that happens, these two elements are redundant in every household. And then every household sends these meter readings to the blockchain. The blockchain then could check the signatures of the smart meter to ensure that the calibrated smart meter is an official one, and then the blockchain could calculate the netting. Every household would trust the results and they could be used for settlement because it has been calculated on the blockchain after all. However, this is a privacy nightmare. All household energy consumption data is public on the blockchain, and that allows detailed insight into customer behavior, as we explained earlier in this talk already. So this leads us to the following problem statement. How can we calculate the netting with blockchain properties, but without giving up user privacy in the process? To address this problem, we now introduce a privacy-preserving energy sharing protocol and system design. Here you can see our an extension of the naive blockchain-based architecture we just showed. And as you can see, we have one new entity that's a netting entity. So we have the smart meters and the household processing unit, and they are in every single household. Then we have this netting entity, and this is one component. It exists once globally. And then we have a blockchain, and blockchain clients are run by all the households and by the netting entity. The basic idea is now that this new netting entity collects the consumption data from household processing units and then calculates the netting by itself. It then sends the netting result to the smart contract, and the smart contract can verify that this netting happened correctly, but it somehow is able to do it without learning about the consumption data. Now, this sounds like a good idea, but how is this even possible? For that, we introduce one enabling technology, and that's a bit of background now. So ZoKrates is what it's called, and it's a framework for zero-knowledge verifiable off-chain computations. And what it allows you to do is that you can write a high-level program in a custom domain-specific language, and you can run that off the blockchain. Then you can generate a constant size proof, or rather short proof, that attests that your execution that was performed off-chain happened correctly. And then you can send this proof to the blockchain, and the blockchain will verify that your computation actually happened correctly. And what's so special about these proofs is that you can optionally hide inputs to your program that were used in proof generation, and they do not have to be exposed to the blockchain for validation. So internally, ZoKrates uses zk-snarks as a verifiable computation scheme to realize these properties, but it makes it much easier to use, and it also generates contracts that you can then simply use to verify proofs from the Ethereum blockchain. So with the introduction of that background, I think the basic idea behind this approach probably becomes clearer. The basic idea is that the netting entity calculates a netting and then proves that this calculation happened correctly. However, it needs to do it in a way that everybody in the system can be sure that the correct consumption data was used as inputs, but without exposing that consumption data on the blockchain to the smart contract. And this can happen through zk-snarks as they are realized in used by ZoKrates, for example. And now let's go through the protocol again, and I think it will become clearer how it works overall. The smart meter first collects consumption data and additionally calculates a commitment to this consumption data. And then the raw data and the commitment are sent to the household processing unit. The household processing unit sends the commitment to the consumption data to the smart contract, and the smart contract again can check whether the smart meter is actually an official smart meter, and then it just stores these commitments. And the household processing unit in parallel sends the raw consumption data to the netting entity. The netting entity then does several things. First, as already explained, it calculates a netting result and also proves that this netting happened correctly. And what's important is that the proof also shows that the raw data that the netting entity used belongs to the values, or are the values, that the household processing unit previously committed to on the blockchain. So what that gives us is the guarantee that the netting entity did not make up any data for its calculation, but actually used what it has been reported to by the household processing units. The netting entity cannot directly publish the netting results on the blockchain, because then again sensitive data would become known to the public. But the proof that the netting entity generates is only really meaningful if it somehow contains or captures the information of what the netting result was, because otherwise, if nobody learns what the results were, then the computation wasn't successful or meaningful in the first place. So the little workaround we use here is that the netting entity actually in the process, in its off-chain program, also calculates a commitment to the netting result and publishes that commitment to the netting result on-chain in the smart contract. So again, this is not sensitive information, but it's kind of a fingerprint of the result, so it can be used in checks later on. And in the end, the netting entity sends the proof together with these output commitments to the smart contract. The smart contract then verifies the proof that everything happened correctly, that the netting was calculated correctly, and that the correct input data that was previously committed to by households was actually used as netting inputs. And then it stores the netting result commitments in the smart contract. The household processing units after that receive the results of the netting calculation from the netting entity. And they can then use these results and calculate the commitment, recalculate the commitment, and compare it to the values on the blockchain. And that way they can be sure that the netting entity honestly reported back the results, and that these results are the results that were committed to previously on the blockchain. And we can then be sure that this netting was actually performed correctly because the commitments to the results were computed together with the netting itself as part of the off-chain computation that we have proven correct. This was the basic idea, the basic intuition behind our privacy-preserving netting approach. In the paper, we describe this in much more detail, and we provide an in-depth process description, as you can see on the right here. Together, the system and protocol design is considered our second main contribution. To show viability of our approach, we provide an open source implementation of the privacy-preserving energy sharing solution and evaluate it in the context of a German national research project. Here you can see the architecture overview that also shows the component involved in the implementation in much more detail. It's pretty much a standard stack, you could say. Probably most interestingly, the netting entity runs a server that obtains all the input data, talks to the blockchain, and then calculates a netting and uses ZoKrates to verify the netting and do all the other calculations in an off-chain computations that we previously explained in the higher level conceptual overview. What's important to note here, and that's where the implementation is a bit different from the concept, is that the netting entity first calculates a netting, and then in the provable off-chain program, the ZoKrates program, only verifies the netting's property, so correctness, Pareto efficiency, and fairness, and does not calculate the netting itself. The idea is kind of similar to finding a solution to an NP-hard problem somewhere and then just having a verifier that checks the solution. Here you can see just a screenshot for illustration of the user interface. There is sensor data that you can see on your user interface. So that's what the end user in the household sees. You can see how much energy you saved overall. You can even see the virtual transfer ticker that shows the amounts of energy that were transferred between households. For the evaluation, we did that in the context of a larger German national research project, which is called BlockPV. And the goal in the project was that the netting interval is 15 minutes. So every 15 minutes, the energy production and consumption in the community should be netted using our algorithm. And we had a target of 100 households because that's the size of the test bed that we have. As it turns out, with any further optimizations, everything happened within 9 minutes and or slightly above 9 minutes, which was totally fine. But after evaluation was done, we also figured out that there's a low-cost optimization just by using a more elegant commitment scheme based on Peterson hashes or the MIMSI hash function that could bring this time down an order of magnitude, most likely. The on-chain verification is very cheap for few households. That's because you have this fixed cost for verifying a proof, which is always constant size, no matter how complex the computation, but then grows rapidly because the smart contract has to retrieve all the result information and store it on the blockchain as well. However, this is not really a problem in our case because in that private blockchain, we could have much higher gas cost and still be fine. Let's come to the conclusion now. We made 3 main contributions. First, we provide a characterization for desirable netting results and also developed and provide an algorithm to compute such nettings efficiently. Then, most importantly, we proposed a system and protocol design for privacy preserving and trustless community energy sharing. And then we implemented an open source prototype of this proposed system for the Ethereum blockchain using the ZoKrates framework and evaluated it in the context of a German national research project. As a more general result, and I think that's a very interesting takeaway, is we showed how ZoKrates-based off-chain computations can be combined with a commitment scheme to execute calculations in a group of mutually distrusting pairs with blockchain properties and privacy protection at the same time. And I think this is a very intriguing result, that you can do these computations and have blockchain properties, but not give up privacy of your users. Here's a bit of a summary. This was a brief overview, and for all the other details, please consider the paper or ask in our Q&A session that we will have during the virtual conference. Feel free to reach out whether you have any questions or whether you'd like to learn more or collaborate even. My contact's on the right side, and my co-authors are also happy to answer any requests. So thanks for watching. Hope you enjoyed it.